Yes. Okay. So thank you everybody for being here, and thanks to the organizer for inviting me. So the title of this workshop is Tropical Geometry, Moduli Spaces, and Matroids. I'm gonna focus on the matroid part of it, but if you see some interesting connection to moduli spaces and tropical geometry, please do let me know. Okay, so I'm gonna talk about positroids. So what are positroids? Positroids is just positive matroids. So let's see what it means for a matroid to be positive. And I'm gonna start with by recalling the definition of a matroid. So there are many different definitions of a matroid. The one that we are interested in today is by the rank function of a matroid. So a matroid is given by the data encoded in a rank function, which takes the subset of a finite set to the integers. And it's such that, well, we want the rank to be a positive number and smaller than the cardinality. It satisfies a submodularity condition. So if we have the rank of A plus the rank of B of two sets, then this is going to be bigger or equal than the rank of the union plus the rank of intersection. And then we want the rank to satisfy some monotonicity property. So if we add an element to a set, then this rank will be between the rank of A and the rank of A plus 1. Okay, so how can we construct a matroid? If we have a K by N matrix with entries in a field K, then we obtain a realizable matroid over the field K. And this rank function is defined by taking the rank of the submatrix, which has columns indexed by the set that we are considering. Okay, so now let's see what is a positroid. So for a positroid, we want some positivity condition. And this positivity condition will come from the space where we ask the matroid to be realized. So we say that the totally non-negative Grassmannian is the subset of the Grassmannian where all the Plucker coordinates are positive. Well, this is not exactly correct because all their points in the projective space. So we want all the Plucker coordinates to be of the same sign. How can we think about this intuitively? So if we have a point in the positive Grassmannian 2n, then we can see the columns as vectors in a two-dimensional plane. And the positivity condition corresponds to the fact that the vectors are ordered in a counterclockwise order within the upper, let's say, 180-degree plane. So here we have V1, V2, V3, V4, V5. In particular, we see that positroids really depend on the order that we choose on the elements. Okay, so yeah, as I mentioned already, a positroid is a matroid that can be realized by an element of a totally non-negative Grassmannian. Okay, so in general, we don't really like realizable, or maybe you like them, but realizable matroids are a bit complicated. We know that the realization space of a matroid can be as ugly as possible, and we cannot characterize the realizable matroids. So we cannot add an axiom to the ones of matroid to just restrict to the class of realizable matroids. So now we are adding an even weirder restriction. And you might think, okay, this class is going to be even more complicated to describe. But this positivity condition actually makes things much easier. So positroids are in bijection with many combinatorial objects, among which are Lie diagrams, Playback graph, bounded affine permutations, Grassmann necklaces, there are many. And they have all been introduced by Poznikov in 2006, where he also introduced the positroids. But the realization space of a positroid is also much nicer than the one given by a matroid. So we can consider the realization space of a positroid inside the totally negative Grassmannian, which is the, let's say, natural space where we study positroids. So this is all matrices such that the associated matroid is the given positroid. And these positroid cells are as nice as you can hope for. So they're homeomorphic to open balls. and they give a CW decomposition of the totally non-negative Grassmannian. But even if we look at the realization space inside the Grassmannian, we can study the open positroid variety, which is the set of all vector spaces whose associated positroid is the given positroid. And this is a smooth variety. Okay, so note that here, I'm not saying that the matroid associated to V is the positroid, but I'm actually considering a slightly larger set. So we want to construct the matroid of the set P, and then I want to see what is the smallest positroid containing that matroid. This is called positroid envelope, and I'm claiming that this positroid envelope is equal to the positroid P that we are fixing. Okay, so let me tell you a bit more about the combinatorial structures of positroids. And what I'm going to tell you today is the relation with bounded affine permutations. So a bounded affine permutation of size n is a bijective function between the integers, which is periodic. So pi of I plus n is pi of I plus n, and it's bounded. So the image of I is between I and I plus n. Okay, so yeah, as I said, bounded affine permutations are in bijection with positroids. And how does this construction work? So we take a positroid P, and then we want to take the image of I is going to be the smallest j, such that I is in the linear span of I plus 1 until j. So let me do this with an example. Yeah.
How is it different from the map from 0 to n minus 1 to also from the bijection from 0 n minus 1 to 0 minus 1? Right, because this is periodic condition gives you.
Yes, but now we want. Yes, but now we want the image. It's contained in n plus 1 elements. So an equivalent definition is decorated permutations, which are just normal permutations, but the fixed elements are decorated, so they can either plus or minus. Yeah, so we just have slightly more information than a normal permutation. Yeah. Okay, so let's consider, for example, this positroid. Okay, so I hope you're all familiar with this notation. Here, this is a rank-free positroid, and we see the points as points in projective space. We cut with a generic plane. We get this picture. And let's see how we can construct the bounded affine permutation of this positroid. Okay, so we want to map the elements between 1 and 9. Okay, so for example, 1 is not contained in the linear span of 2, but it's contained in the linear span of 2 and 3 because they're contained in the same line. So the image will be 3. 2 is not containing 3, 4, 5 neither because they span a line. So we have to go to 6. Similarly for 3, 4, 5, 6, 7 is not enough. We have to go to 8. 4, we just need to go to 5. So let me. Okay, this is not very visible. Okay, 5. So when we have 6, 8, 9. For 6, we just have to go to 7. 7, we need to go to 2, which is 11, because we want to take the next. 8, we go to 10. And 9, we have to go to 13. Okay, so I hope this construction is clear. Okay. And maybe one thing that you can see from this fact that bounded affine permutation define uniquely a positroid is that we are really only looking at cyclic intervals. So that's what that's like the information that we care about when we study the rank of a positroid. So then a natural question is, what are the minimal rank conditions on cyclic intervals that uniquely define a positroid. Do I really need to know all the information of every cyclic interval? And the answer is no. So a first question, this is still not going to be a minimal family, but the first natural question, natural answer is given by essential sets. So I'm going to just fix the rank of cyclic intervals that are somehow maximally dependent. So you can think of them as like flat cyclic intervals. So yeah, the essential set of a positroid are all pairs Rij, such that R is the rank of the cyclic interval Ij. And if we remove one element in the beginning or one element in the end, we still have the same rank. So these elements are going to be dependent. But if I add one more element in the exterior, then my rank is going to increase. Okay, and intuitively, you can think that this is like sufficient information, and indeed it is, because we can compute the rank of every cyclic interval from this information just as a minimum. Okay, but now you might say, well, if I know the whole rank function and then I have to compute like what are these intervals, that's not going to help me much because I anyway still need the whole rank function. So how else can we compute essential sets of a positroid? And there is a nice way of computing essential sets of a positroid from the corresponding bounded affine permutation. Okay, so let's follow the recipe to do this. So we start from a bounded affine permutation. We want to represent it as a diagram. So okay, so you should think of this diagram as the rows label rows, but the numbers in the columns actually label antidiagonals, because we know that the image of I is anyways going to be bigger than I. And now I want to add a dot when in the image of a permutation. So 1 is mapped to 3, 2 is mapped to 6, which is going to be here. This is the antidiagonal 6. 3 is mapped to 8, which is here. 4 is mapped to 5. 5 is mapped to 9, so 5, 6, 7, 8, 9. 6 is mapped to 7. 7 is mapped to 11. 8 to 10. 10. Is this correct? Yes. And 9 is mapped to 13. Okay, so let me check that I did this correctly. Okay, yes, perfect. Okay, so this is the first step. The second step is we want to shade whatever is to the left and in the antidiagonal, sub-antidiagonal of a dot. So here we shade these cells and these cells. Here we have this, and so on. And we do it for every dot. And one thing to notice is that these rows should be thought as like identified. So if I go down here, I have to continue up here. Okay. Okay, now we have some components which are not shaded. So here we have this square. Here we have this square, this square, this square, this square, and this. And okay, maybe I didn't choose the best example because in general, I'm going to have bigger components. But I want to choose the upper right corner of these connected components. Okay, so now here I get this is going to be the interval 1, 3. This is going to be the interval 4, 5. Then we have 4, 7. We have 6, 7. And then we have 8, 1. And then we always like kind of artificially add the whole cyclic interval 1, 9. Okay, so from here you can start to see that, for example, 1, 3 is an essential set and they lie on a line. 4, 5 is an essential set, they lie on a point, 6, 7, and so on. But still, in order to actually draw this picture, I need to know what is the rank of this essential set. So the next step is to compute the rank. And how do we do that? We look at each essential set, and then we want to look at this kind of trapezoid thing. So on the right of your essential set, and we count the number of dots. Yes, sorry.
So 4, 7.
Yes, so now I'm gonna get to it. Yes, exactly. So, okay, 1, 3 has rank 2, and you can do it for all of them. So 4, 5 is gonna have rank 1. 4, 7, for example, which is an interesting case, has rank 2. 6, 7 has rank 1. This is 2, and this is 3. Okay. Yes, I'm gonna get to your question. But the idea is that, yeah, 4, 5, 6, 7 is still gonna be an essential set. And so we actually construct it in this way, even if it's not really necessary in this picture. Okay, so this is a nice, fun game, I guess, to compute the essential sets if you know what is the boundary defined permutation of your positroid. What can I actually do with this essential set? So, for example, I can describe a matroid polytope. So we have seen already the matroid polytope in a couple of talks. So we know it's the convex hull of a indicator vector of the basis of a matroid. If it's a positroid, it's very nice. So it's defined by inequalities on cyclic intervals, again, reinforcing the fact that we only need to know rank conditions on cyclic intervals for positroids. And okay, so now we have that the positroid polytope is gonna be defined by only the rank conditions on cyclic intervals defined by these essential sets. Okay.
There's exactly the pattern.
So no, so we have to look at actually connected essential sets. So for example, this 2, 4, 7 will not be a connected essential set, and it will not be a facet because, of course, it's already defined by this. Yeah. Okay. Okay, but now you might say, okay, anyways, we are still always starting from a positroid, which is given in some way, and we compute essential set. What if I want to give you a family of rank conditions on cyclic intervals, and I want to know if these are the essential sets for some positroid? And we can actually do that. So we have that this axiomatic characterization of essential set is really similar to the rank definition of matroids. That's why I recalled it in the beginning. So let's look at it. So we have a family of pairs of cyclic intervals with a rank. It's the essential set of a positroid if, okay, first of all, we want the rank to be between 0 and the cardinality, as we want it here. We have a strict inequality because now we want our sets to be dependent. So the rank will be strictly smaller than the cardinality. Yeah, then we have some monotonicity conditions. So if we have two essential sets contained in each other, then we want the ranks to be, the difference of the rank to be positive. And then we also have some submodularity condition. Now I can only express these conditions in terms of essential sets. So this become a bit less nice than just this one line. But So we have to consider two examples. If our cyclic intervals do not intersect, then I want to look at the smallest essential set, which is contained. Let me change color. Which is contained in this difference. And then I want to look at the smallest essential set, which contains this union. So this is going to be R3, I3, J3. And this is going to be my R4, I4, J4. Yeah. So we have that this condition has to hold for these essential sets. Okay. So yeah, once again, we feel like not all essential sets are necessary. We eliminated some of them with a connected essential set. I didn't give you the definition of them, but this doesn't eliminate too many essential sets. So so how can we actually, okay. Positroids are defined, for example, by a bounded affine permutation, which is a linear amount of information. We have n plus one vector, sorry, an n vector. Or it's defined by Grassmann necklace, which are n sets and so on. So these essential sets are in general going to be in the order of n squared. So how can we actually reduce to only the minimal essential set? And these are the essential sets contained in the core of a positroid. So the core of a positroid is the set of essential sets which have positive access. So how should we think about this positive access? We want to, okay, so maybe let me do it here. The axis should be thought about as the number of points we are fixing with that condition given by the essential set. So for example, 1, 2, 3 has 3 elements and has rank 2 and does not contain any other conditions. So this will have access 1. Now, if we have something, for example, like 1, 2, 3, 4, then we will have an essential set 1, 2, which has access 1. And then the set 1, 2, 3, 4 has access 4 minus the rank, which is 2, minus the access that we are already counting. So this is really intuitively how many points we are fixing with that condition. And okay, so the core actually does give the minimal set of rank conditions to define a positroid. And how can we prove that we can recover the positroid? So we could give an algorithm to do this. So first of all, let me notice that here, this 2, 4, 7 will not be in the core because its axis is going to be 4 minus the rank 2 minus the axis of 4, 5, which is 1, minus 1. So this is 0. So we can forget about this. Okay. And now we add these rank conditions inside my grid. So here we will have a 2, we will have a 1 here, a 1 here, and a 2 here. And we can run an algorithm which will retrieve this permutation. So what's the intuition behind this algorithm? We start from the essential set with smallest rank, so these 2. And okay, so we know that this rank on this side has to be 1. So we want to add, since we have 2 rows, 1 dot on this side of the triangle. So we will add it here, same for here. And then we can do the same for the rank 2 condition. Okay, maybe. Okay, so now we know that all the other points will have to lie on the right-hand side of these triangles. And we know that the positroid has rank 3. So in some way, yeah, we want to put them so that the positroid will be of rank 3. So for example, for 2, okay, this will count as 0, 1, 2. But now here I already have a point. So this does not count, and this will be 3. Okay, so this is not very intuitive, but there is an implementation of the algorithm on my website. You can just give it some rank conditions, and it will run and give you the permutation, and it will get back the right permutation. Okay, so I'm not gonna draw it now. Yeah. Yes.
Coincidence that there's always two squares when you have a 2 in the square and 1 square before it, if you have a 1 in the square, or is that something that always?
No, yeah, it does not always happen. So, for example, in this case, I will have something like this. So 1 goes to 2, so my dot will be here. And then, yeah, but 2 just needs to go to 4. So, okay, no, this is not, okay, let me rename things here. Okay, let me do it opposite. 1, 2, 3, 4. Okay, so I will start from 3, which goes to 4. And now 1 will go to 3. Okay. No, I cannot construct an example, but no, in general, yeah, it's not the case. Okay, so I mean, I'm gonna lose some information with the core. Of course, we are restricting a lot the set. As I told you, in general, we have around n squared over 30 essential sets for a positroid on n elements, and the core has cardinality at most n. But we still can retrieve some information about the positroid. So for example, we can compute the codimension of a positroid cell defined by a positroid in terms of the core. And this is gonna be given by this formula, which is just what intuitively you would think that the codimension should be. Okay, so maybe an open question, which we didn't solve, is can we axiomatically define the core of a positroid? So if you give me a set of pairs of ranked cyclic intervals, can we give conditions for this to be the core of a positroid? And yes, the sum is over the core. Yeah, I didn't write it. Yes, the sum is over the core. Also because here we have the x's, so all the other terms would go to 0. Okay, so yeah, that's all I wanted to say. And if you're interested, this is how ChatGPT sees this paper. So very hexagonal. And thank you.